Okay, so here's the. Okay, so the videos that you saw were all about circuits. Here we're going to back up a little bit, and we're going to very briefly talk about some of the concepts that lead up to circuits, mostly because I want to establish some vocabulary. We're not going to do any of the sample problems. Yay for you guys. What this unit is, it's a mishmash of material from 4 different chapters. And what I tried to do here, because I've never had time to do the electronic stuff at the level that I would like to someday, what I tried to do was pick out the parts of each chapter that really build to the next chapter so that you get some of the background. In past years, we actually did do the sample problems and some problems from 17, 18, 19, etc. We're not going to this year. You'll have some mostly circuit problems this year. Okay, so the very first thing to know is the concept of charge. So let's just talk briefly about what charge is. All charge is, it's an imbalance of electrons to protons. So if you remember all the way back to chemistry, you remember that subatomic particles have charges. And as long as the numbers match up, everything's neutral. But one of the things that we know about electrons is they're not fixed like things in the nucleus are. So they tend to do squirrely, ornery things like run away, jump onto other things. We get electrons that move. And when we have a surface that has either gained a bunch of electrons or has lost a bunch of electrons, suddenly that surface is charged. So charge is just an imbalance of electrons. If we strip a bunch of electrons off of an object, it has a positive charge. If we add a bunch of electrons to an object, it has a negative charge. And the big part is that we can't make up charge. As we were saying, charge is conserved, just like mass is conserved, just like energy is conserved. We just move electrons around. We don't make them up, we don't get rid of them, we can't destroy them, we can't create them, they're just shuffled. And the other big thing, and something that you have all known since, I don't know, like the 3rd grade probably, opposite charges attract, like charges repel. So if we take 2 positively charged objects, they will move apart from one another. If we have 2 negatively charged objects, they will move apart from one another. However, if we have a negatively charged object and a positively charged object, yay! This is actually really useful. So one of the big applications of that very simple idea, how many of you have ever had the misfortune to have to go to a body shop with your car? Who's run into deer? Who's gotten run into? Who's run into other things? Okay. It happens. It just happens. If you have to get a car painted, so how many of you have spray painted anything? Good. I don't want to know what, maybe. So, you know that when you spray paint something, you end up with paint on your hands, there's paint over here, there's paint over there, there's a lot of waste. And one of the big things that has been done in the auto body industry is they use what's called electrostatic paint booths. Guess what that means? It means that the vehicle or the surface being painted is charged, and I believe it's conduction charging. We'll talk more about different kinds of charging. I'd like to know more about this actually. But anyway, the vehicle is charged, and the paint particles are charged with an opposite charge. So guess how much overspray and waste of paint you have? None. Because every single paint particle goes whoom, and just heads for the car. It's brilliant. It's totally brilliant. Yeah, I mean, it's a huge thing. And it's just an application of this very simple principle that opposite charges attract. So, we know what charge is. It's either excess electrons or a loss of electrons. And some things will let those electrons flow more easily than others. You've talked about conductors and insulators in chemistry. We know that things in the D block, those transition metals, all metals actually, tend to be good conductors. They let things flow. Things that do not allow the flow of charge are insulators. So, anything can be charged by contact. You can get a positive or a negative charge by contact. So if I am getting a contact charge, you have all done this, by the way. You have all gotten a contact charge.
Yeah.
Yes, you have. Especially in the winter, when the air is dry and your skin is dry, and you shuffle around the house in your big woolly slippers on the carpet, and then you touch the doorknob. What happens?
Static.
Static. You get a shock. That shock is electrons making the leap from your body, because you have picked up additional electrons, to the metal of the doorknob, which is a good conductor. And so you are charging that doorknob by contact.
Wait, where are the electrons?
The electrons, you pulled them off the carpet. They're now on your body. You have a reserve of electrons. And you are putting them, when you touch the doorknob, you're transferring them to the doorknob. That is a contact charge. Two surfaces are in contact and the electrons flow onto the surface or off of the surface. Now, you got your charge before you touched the doorknob the same way, by contact. How? In your big woolly fuzzy slippers shuffling around the house. If only you would lift your feet. Jeez, oh pezo. You pulled them off the carpet through your sort of mechanical action of shuffling across the carpet. And wool is fantastic. We're not going to have time in here to talk about the whole, there are some things we're not going to cover, but there's a list. Triboelectric charging is the charging by rubbing two surfaces together, and we'll do some triboelectric charging here. It's contact charging, but there is a list of triboelectrics, and it's the ease with which things either gain electrons triboelectrically or give them up. And some materials are really good at giving them up, and some materials are really good at gaining them. If you put those two together and rub them together, you get a tremendous charge. How many of you have stuck a balloon to the wall with static electricity? Okay, we take a balloon, we rub it on our head. You are triboelectrically charging it. Your hair, and I think your hair sheds electrons and the balloon gains them. I'm not sure, I'd have to look it up. And you can look at a triboelectric series to determine that. Okay, so that's contact charging. The other way to charge things is what we call, this is actually the details on conduction. Contact charging or conduction. So we have a neutral object and a charged object. Electrons flow from one to the other. And usually what we say is that the excess charge leaves the original charged object. So we usually think of it as all of the electrons jumping off the first charged object. If you charge something by conduction, a contact charge, it's got the same charge as the other thing. So if you have a negative charge and you touch the doorknob and you charge the doorknob will now have a negative charge because you've just transferred electrons to it. So here we have this our little box, and all that you see in that little box, there is a metal rod hanging down from the top of the box. Connected to that metal rod are two very, very, very thin pieces of aluminum. And when I touch the ball at the top, it's all metal, something happens to those two aluminum plates. So let me get another picture as I do this. I don't know if you can see that they've moved apart a little bit. And as soon as I take this away, it goes away. The effect goes away. So what we've done is we've transferred electrons. We transferred electrons from the rabbit fur to that rod. And then, retake. We transferred electrons from the rabbit fur to the rod. and then from the rod to the little metal bar in the device. And those plates now have the same charge on them. And they are such thin aluminum, they're light enough that they'll actually move apart in response to that same charge. But that is conduction charging, because it's contact charging. We had conduction charging, now we've got induction charging, and here we have two objects that are not touching. So what happens, you have to have a third object, and we call that ground. And if you have, how many of you know where the ground stake is around your house? How many of you have ever seen a ground stake? You know what that is? It's up to like a 4-foot chunk of solid metal that gets driven into the ground, and it grounds your electronics. Have you ever heard have you ever heard someone described as being well grounded? You know, I like that kid. She's really well grounded. She's just real, you know, real steady. Okay. Ground is a reservoir for electrons in this sense. It's the ability to sort of sink into something. We usually use the earth as a ground. That's why we call it ground. Duh. You can use other big things as grounds. If you're jumping a battery in a car, you usually use the car's frame as a ground. You know, you can use some other large thing that's got lots and lots and lots of electrons and can accept some more electrons if it needs to. So when you charge by induction, here we have an uncharged object. Okay. If we take a negatively charged object and we stick it near that uncharged object, you're going to get basically an area of partial charge. So what we show here, and this is the typical one, it's shown in your book this way, all the little positives line up on one side and all the little negatives line up on the other side. There's just one problem with that. What are the positives? In reality, they're the protons. They don't move. They're not like all the protons aren't moving to one side of the thing and then we've got a bunch of empty space with all the electrons on the other side. That would be weird. But metaphorically speaking, we do have a bunch of electrons flowing to the opposite side. So we end up with a region of partial charge. It's kind of like if you go back to chemistry and you think about the polar molecules where they have these regions of partial charge. Well then, if we hook that thing up to ground, and the symbol we use for ground is this. Well, badly drawn, but it's that. It's something driven into the earth. Those electrons will actually vacate the object. They will actually flow off the object. They will flow into whatever that ground reservoir is. And then what you have is an object that has a net positive charge. Okay, so it's got a net positive charge. You can now remove this negatively charged object that you used to charge it, and it's still got a positive charge. So that's charging by induction. The big thing to know, when you charge by induction, there is no contact, but you have to have a ground. You have to have a place for those electrons to flow to. Okay. And when you charge by induction, the charges are going to be opposites. So whatever you used to do the charging is going to have the opposite charge of the object which is now charged. Polarization, it's just like induction, but it's really only a partial charge. That's all we need to know. We don't lose electrons, we don't gain electrons. They just line up in little rows like kindergartners going to the bathroom. Okay, now, that was the start of chapter 17. Electrical force, Coulomb's law. We're not going to do any of this. Ha! But what I do want you to know is this. You understand that charges attract and repel. We talked about like electrostatic paint booths in a body shop. You can actually figure out the amount of force. I know, you're all excited in a Twitter because I could do force calculations again? I'm sorry. Electrical force is given by this whole thing, and K is the charge, No, K is Coulomb's constant. Q1 and Q2 are the charges, and R is the distance between them. We're not going to do this. I know you're heartbroken.
So we just need to know.
You just, I mean, know that electrical force is the force between two charges. And what I'll tell you, because if you are going on, if you're going to do a lot more, I don't have any future electrical engineers in here this year. If you were heading into electrical engineering, you would do a lot of calculations with point charges, and you can do multiple point charges. You know, if I have these 4 charges, figure out the net charge on this, and it's a lot like doing net force calculations, but uglier. You know, so there, something to look forward to. Okay, electrical force, it is a vector. If you're going on in physics, you'll need to know that, but you really don't. You know, it can be attractive or repulsive based on whether you're looking at 2 like charges or 2 unlike charges, and we can do all kinds of fun stuff with that we're not going to do. Electrical fields exist. That's it. We'll pick it up tomorrow.
They exist.
Okay.